When calculating centripetal force, we want to think back to our normal way of calculating force. Right? Newton's second law told us that force was equal to mass times acceleration. Well, if we want to calculate a centripetal force, that's just mass times centripetal acceleration. And we also had the equation that centripetal acceleration was equal to our tangential velocity squared over r. So we'll go ahead and substitute that in. And calculating centripetal force would be mvt squared over r. And that's our equation for centripetal force. It comes out in newtons, just like anything else. And centripetal force, by definition, is the force that keeps something moving on a circular path. So when you calculate this, this is the force that's constantly pulling on something and keeping it moving in a circle. One very important thing to think about when we're solving a problem. Let's say that we have just a string and some mass on the end of it. And this mass is spinning around in a circle. So our centripetal force is keeping it moving in a circle. Well, what's keeping it in a circle? Well, it's the tension on the string that's keeping it in a circle, right? If this string wasn't here, this wouldn't move in a circle. So something very important to realize is that the centripetal force is never a force on its own. It is always a force caused by something. So in this case, it's caused by the tension in the string when it's spinning around. So we would really say, if we were setting up a problem, we wouldn't say centripetal, we would say something more along the lines of this rather than this equation. We'd say that our force of tension is our centripetal force, and so our force of tension is equal to mvt squared over r. So in our Newton's second law calculations, like sum of our forces equals ma, this centripetal force part actually goes on the ma side of things rather than on the forces side of things. The force is always an actual thing, a tension. Could be gravity in future situations. It's whatever's causing it to move in a circle, and that's equal to its centripetal force, which is mass, times our centripetal acceleration. Now let's think for a minute about which direction this would go. All right, so we have our circle here. Let's go back to the example of something on a string. So we have our object on a string there, and it's going to be moving around in a circle like that. Well, we have a couple different quantities here. Right, we have our tangential velocity that's going that way. We have our radius, r, of our circle. We also have centripetal acceleration pointing towards the center. Now, keep in mind that centripetal force is the force that keeps it moving in a circle. Well, remember when we talked about centripetal acceleration, we said that it was always kind of accelerating things back towards the center from every point around the circle. So if it's going to accelerate back towards the center, then what that means is that our centripetal force also has to always point back towards the center of the circle. So our centripetal force is always towards the center of our circular motion. This is because that centripetal force is causing that acceleration back towards the center. So for a sample problem, we want to know what force is exerted on a 900 kilogram car that is moving on a 500 meter radius circle, or 500 meter radius turn, moving at 25 meters per second. And we also want to know what is the coefficient of friction needed to keep it on that turn. So start with what we know. Well, what we know is that we have a mass equal to 900 kilograms. We have a velocity of 25 meters per second. And since that's its velocity going around a circle, we could call that its tangential velocity. We also know that we have a radius of 500 meters. So there's all our known values out of there. What we're solving for? Well, we're solving for what is the force, so centripetal force. And we're also solving for what's the coefficient of friction. So our plan. Well, first, centripetal force, right? So here's our equation. Centripetal force is mvt squared over r. Okay, so we could easily solve for that because we have everything. So solve for centripetal force. And then to get friction, well, what we have to realize is that for a car to move on a circular path, so when it moves around a circle, something has to keep it moving towards the center to keep it in the circle. If it didn't, it would slide off the road, right? Instead of going on this nice circular path, it'd kind of slide off. Well, what keeps it on the road? Friction does. So it keeps it in a circular path. Friction keeps it in a circular path. So we know that my force of friction has to be equal to my centripetal force. And from there, solve for our coefficient of kinetic friction. So solve for centripetal force. Well, we have 900 kilogram car moving at 25 meters per second squared divided by our radius of 500 meters. So our centripetal force equals 1,125 newtons. And then, so that's answer 1. That solves for centripetal force. And then we also said that our centripetal force was equal to our force of friction. So our force of kinetic friction in this case is going to equal 1,125 newtons. And our force of friction is coefficient times normal force, which is 1,125 newtons. And our normal force, in this case, because we're on a nice flat surface, is just going to be equal to gravity. So that's mg. It's 1,125 newtons. So our coefficient of friction is going to be equal to 1,125 newtons divided by mg, so divided by 900 kilograms times 9.8 meters per second squared. And if we do that, we get a coefficient of friction of 0.13, which is a very realistic number, right? Less than 1 seems along the lines of most of our coefficients of friction.